Okay, in this video we're going to introduce the idea of what's called summation notation. Summation notation is a way to express summation notation is a way to express a repeated sum where we're adding something up over and over for multiple terms. So we begin with a definition here. Let A1 up through AN be some sequence of numbers. That could be just a list of numbers. It could be, it's very often, a list of numbers that's defined in terms of some function, some formula. Then the sum, which looks like an E, that's actually the capital Greek letter sigma here, right, of AK, that's usually our sequence describer, as K goes from 1 to N. What that notation means is you start with K equals 1, that would be A1, plug in 1 for K, then you add on, you plug 2 in for K, and 3 in for K, and so on, all the way up to the very last term, A sub N. Now, that notation there, sum of the, as K goes from 1 to N, the sigma there is the sum, that big E-shaped letter, that's the symbol for sum. The 1 down on the bottom there is our lower limit. The N up there, that's the upper limit. That's the number it goes up by. And in a sum like this, you're always incrementing the variable by 1. So K is an integer. It's going to increment by 1 each time. A lot like maybe some of the for loops that maybe some of you have done with some programming before. It's kind of a similar idea as that. And the variable K is the index variable. And a lot of times with sums, we tend to use variables I, J, and K for whatever reason for our index variables, I, J, and K. And then the AK, which is the thing inside the sum, is often represented as some function of K. A couple of examples, 3K plus 1 could be your expression inside the sum, or K squared, or 2 to the K. Those are just a few examples of summation notation, of some of the things that can go inside of it. So what we want to look at now are some examples working with summation notation. First, just kind of understanding what it is. It is a tool that we're going to come to make use of as we move forward here and tackle the problem of area under a curve. So we're going to be making use of sums, and if you eventually go on and take Calculus 2, it's something you're going to see again as well. We work with a lot of sums and stuff in Calculus 2. So here we're asked to compute each sum. So here we have the sum as K goes from 1 to 6 of the expression 3K plus 2. What summation notation means is you're going to start, plug the first number in this case 1, into the expression for the variable. In this case it's K. So we plug that in for K, and that would give us 3 times 1 plus 2, and then plus, and then we increment K, make it 1 bigger. So K becomes 2, and then increment, K becomes 3, then K becomes 4. And you'll have to excuse me here, I think I hit the wrong button there. And so eventually K becomes 5, K becomes 6. And so then you multiply all that stuff out and add it up, and we'll get that the sum is equal to 75. So at this point, you're just taking 3 times 1 plus 2, which would be 5, plus 8, plus 11, plus 14, plus 17, plus 20. Add all those up, and we get that the sum as K goes from 1 to 6 of 3K plus 2 is equal to 75. As a second example, consider the sum as I goes from 0 to 8 of I squared. So here we're starting, this time our lower limit starts at 0, and we're going up to 8. So that would be 0 squared, plus 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared, plus 8 squared. And we'd add all of those up. We'd add all of those up, and when we do, we'll get 204. And my thing, once again, didn't pause. Didn't have my pause break yet, sorry. That'll be 204. So that's 1 plus 4 plus 9 plus 16, all the way up to 64. And then one last one here. Sum as j goes from 0 to 7 of 12. So this time the variable isn't showing up inside of the sum. That means it's a 12 every time. But j is still going to start at 0 and increment to 7. So j is 0 would be 12. And then another 12 for j equals 1. And 2, 3, 4, 5, 6. And then as j goes to 7. So it ends up we actually have 8 12s here because we're going from 0 to 7. If it was 1 to 7, we'd just have 7 12s. But we have 8 12s, which is just 8 times 12, or 96. So this is just kind of a brief introduction to working with sums. What we're going to look at in the upcoming video is how we can, or some of the summation properties we have, some of the things we can do with sums, and how we can use that to talk about computing sums like this. Sum of the I-squareds, 0 to 8, not that big of a deal. But what if the sum had been going from 0 to 80? Who wants to sit down and write out all 80 terms and add them up, even if you have a calculator? Even if you had a calculator, who really wants to do that? Or what if we wanted to do this sum from 1 to 100? Again, yes, you could plug those into a calculator, but who really wants to sit down and do that, even putting them in term by term? So we're going to be looking at some ways that we can evaluate these things with some summation properties. That'll come up in the next video.